Hello, everybody. We are at the end of day 6. I can't believe it. I feel like these days have been flying by. So tell us in the comments, how was today? I see Cassandra in there. Christy, how are you feeling here at the end of day 6?
Oh, feeling awesome. Excited to see what they've been working on. And I know we've got some fun things to pull up today. So it's going to be a great show.
Definitely. And we have a really amazing expert presentation to end our week. But I do have a couple announcements from the space team's crew. So right now, if you are in spacecraft, I encourage you to save your work because there will be a reboot of the server now during this webcast. So if you're watching this live, save your work because there's going to be a reboot. It will be available by the end. So in about an hour, everything should be back and running so you can jump back in and continue with the different activities. The reason for this reboot, there is a little bit of trouble just on a few teams. The majority of teams seem to be doing pretty well, but with the surface operations mission, some teams are having trouble exploring. And if you are one of those teams, please reach out to the help desk. So if you're in the activity, you can't see your habitat, it just doesn't look right, you're not able to collect those resources to go out, contact the help desk and they will figure out a way to troubleshoot it and get you help. This is a scored activity, so we want to make sure every team has a chance to be successful and to work through this mission. So if in the end we are not able to get all teams to successfully complete this mission, we're not going to count it in the final score. So our number one job though right now is to reboot the server and try to get every team a chance to do this. But we want to know if you're having trouble. Yeah, I see some people are a little bit frustrated. So if you're one of those teams that's like, I can't get this to work right, please reach out to the help desk. They are standing by, ready to go. So our hope is every team is able to do this really, really cool final mission. So those are my announcements. Yeah, so Olivia, she's asking, what do we do if we're never able to do surface operations? So Olivia, please reach out to the help desk. They are standing by, and right now they're going to reboot the server, the spacecraft game. So it's going to go through a little reboot, and hopefully that fixes whatever bug is happening. But they're there to support you. So please reach out. And Olivia, if worst case, if there's a team out there that cannot get this to work, we're not going to score it. But right now our plan is to keep it in scored mission if every team can do it. All right, so with that, let's get on to some fun stuff with our expert presentation. We have a really exciting guest. His name is Benjamin Morell. He is a robotics technologist at NASA Jet Propulsion Laboratory, or JPL, California Institute of Technology, working on autonomous navigation technology for robots flying, exploring underground and in space. This is probably very fitting for this mission. He's the perception lead on Team CoStar, a collaboration between JPL, MIT, and Caltech, competing in the DARPA Subterranean Challenge with a focus on global localization and mapping, as well as detection and location of objects of interest. He's also working on autonomous approaches to small bodies like comets and asteroids. For all those Australian teams out there, he did complete his PhD at the University of Sydney in the School of Aerospace Mechanical and Mechanotronic Engineering. In 2015, he received the Australia to USA American Australian Association Fellowship, which means he got to go to a year at Texas A&M as part of his PhD research. Ben also has a bachelor's in aeronautical space engineering at the University of Sydney, and that was in 2013. So in addition to his core research, he's been involved in all sorts of different activities, including 3D printing and Mars mission simulations, international drone control, and coordinating the Zero Robotics competition, which we heard about earlier this week in Australia, where high school students get the opportunity to send their code to the International Space Station. So that's just a little bit about what Ben does, and I'm so excited to bring him on. So I'm ready to see the comments going. Ben, how are you doing?
Very good. It's cold here on Mars, so nice to see you all. No, just kidding. Yeah, great to be part of this, and welcome to all the space teamers out there. It's super exciting to be part of this program. Just what you're doing with the project at the moment, what you're learning is so cool, and it's a privilege to kind of have a chance to chat to you.
Well, Ben, before we let you go into your presentation, I have a little surprise for you. We had students submit some photos of their team, and I just wanted to share a little bit of who is behind what some of these students that you're seeing in the comments. They're really cool work.
Oh, great.
Here are some of the team photos. Some are very serious. The pic- And
Awesome.
we just, like, love seeing the students that are submitting these habitats and all these different missions, but I have a special photo, though, for you, and the students have been messing with us all week, those Australian students, and they convinced us that kangaroo racing was a real thing. I'm gonna assume it's not, but here they say they photoshopped their faces on pet kangaroos, and this is Cassandra, Keisha, and Sienna. So my question is, one, they're trying to tell us that they ride kangaroos to school and then they do kangaroo racing in Australia.
Oh, we ride in the pouches. It's a form of transport.
That's
That's
what
what
they
Everyone
said.
has a pet one.
see.
I
Oh,
did remember from last time that you were on, Ben, that you told us you did eat kangaroos. So
Mhm.
I remembered that, which is why I took the kangaroo racing maybe a little bit more seriously than I should have.
Yeah, there's some crazy things and there's some not so crazy things. Or it's crazy things that are true, crazy things that are maybe not quite true.
You never know with Australia.
No, that's right.
I love it. Okay, well, Ben, I am going to bring up your presentation right now, and we're going to go off screen, and it's all yours.
Great, thank you. And thanks everyone. So as Natasha was saying, I'm a robotics technologist, robotics engineer. I work on building robots at the NASA Center in California, in Los Angeles, called the Jet Propulsion Laboratory. And what I wanted to share and discuss with you is talking about robotic explorers, which is something that you might have been using in the program where you're looking for resources to support your habitat. Some of you might have been using robots to help you do some of your missions. That's very similar to what we do at NASA, where we are using robots to help us look for resources. And we'll get into a little bit of that. Now, as I go through, I'm going to be asking some questions, and I want you guys to be responding in the chat if you can. So if you're not on it right now, get in the chat, send a message to say hello, and I'll ask some questions, and it'll be great to see if you guys can send through some of your answers or what you think the answers are, some of the guesses there. So robotic explorers, when we go out into space and explore, it's really hard to get humans there. That's what you guys are working on at the moment. And so what we do is we send robots out that can do some of this exploration that's hard for humans. And these robotic explorers can be things like this that we see here, a rover. It can be orbiters that go around planets, such as this one called Cassini that was going around Saturn. And they can be even going beyond our solar system, such as this picture of the Voyager spacecraft. And this is a bit of a family history of the missions from JPL, the NASA center that I work at. Every one of these lines is a different robotic explorer. And the different lines, the different colors are going to explore different planets. You can see there's a lot of them going to Earth, probably one of the most important planets, but they're going to all the different planets, to the sun, to asteroids and comets, and beyond. And all of these are robots. So let's look at some of the planets. And now everyone just going to post in the chat, what's your favorite planet out of these? Let's see if we can get them down. Favorite planet, anyone? Ooh, I was giving away my favorite planet. I think mine's probably Earth, just because it's a really good place to live. But there's some really interesting planets out there, and they're all beautiful and unique in their own way. Okay, I got a few: Jupiter, Neptune, Saturn. Yeah, they're all amazing planets. But what I want to focus on now in this chat is on Mars. Venus, Earth, the planet with kangaroos, that's Earth, definitely. And Mars is a really interesting planet because it's quite similar to Earth. Now, how big do you think Mars is compared to Earth? Do you think it's 2 times bigger? Do you think it's half the size? Do you think it's 10 times the size? These pictures here aren't quite to scale. So how big do you think it is in comparison? Give a chance for you guys
And
to.
Ben, I'm just going to give you a heads up. That's like a 5 to 10 second delay, and so that's why it takes them a second for the comments to come through. Just so you know, they're listening.
Awesome. Thanks, Natasha. And thanks everyone for your answers. I really appreciate it. Okay, we've seen about half the size. That's pretty close. It's about 1/3 the size of Earth. But to give another comparison, the total surface area of Mars, so the total area around the whole planet, is about the same as the total surface area of the land on Earth. So you think you take away all the ocean, or just disregard the oceans, and you're just getting the surface area of all the continents. It's about the same as the surface area of Mars. So it's still pretty big. Now, one of the reasons why we're interested in Mars is because it's similar to Earth, and we're looking to answer a particular question. And that question is there life on Mars? Was there ever life on Mars? Could there potentially be life on Mars in the future? Now, to answer this question, though, we need to work out, what do you need to show that there's life on Mars? What do you need to have life on Mars? And so, what are some of the things that you think might be required for life, or what's required for life on Earth? What are some of the essential ingredients that we need? So, think about what's really important to keep people alive. So, one of the things is water. You all have to drink water. It's a really important part of how we keep alive as things living on Earth. What else is really important for us? One is energy. So the sun is really important, that it brings down energy to Earth. Oxygen, that's a great one there as well. And so there's kind of the stuff we breathe in and out, the chemicals in our atmosphere, but also in the food that we eat is really important as well. So it's kind of like the food, the ingredients, the chemicals that come in are really, really important. And so these are kind of just high level things. We need energy of some sort. We need water, as far as we understand it, and we need some type of the minerals, the elements, the food to feed these forms of life. So this is what we're looking for on Mars. And you can see how this is similar to the resources that you guys are looking for when you're doing your exploration for resources. To keep your habitat sustainable, that's human life that you put there, we're kind of looking for the same thing with our robots to see if it could support life at the moment or past life. Okay, so here's a picture of Mars. And can you tell me, is there water there? It's probably a bit hard to see. We've got some really great answers coming through. Heat, food, wombat stew. Yeah, it's a good option too. Good conversation as well from Barbara. Thanks for that. Yeah. And animals are a really important part of life on Earth as the ecosystem. Now, obviously, you can't quite see trees here on Mars. Can you see water though? Is there maybe water? There's definitely sun, so we got that energy coming in. And what about the chemicals? Are there the right chemicals there for life? It's kind of hard to see. Maybe this is an ice cap along the top. Yeah, a few people might spot that. But we really need to go closer to understand. And that's where the robotic explorers come in. That's the way we can send things to get much closer to Mars so we can learn more about it to see if it's got those important ingredients for life, maybe except wombat stew. And so here's some of the examples of the robots that we've sent to Mars from NASA. There's different landers that go and land and stay in one spot and take different measurements. There's this first test. It's a lander, but this little robot you might see here is a little 6-wheeled rover. And that was what we call a technology demonstration. It's a test to see, can we drive this something that's a little robot on Mars? And that was so successful, it led to more rovers. These are Spirit and Opportunity. That was successful again, so it led to an even bigger rover. This one's about the size of a car. It's Curiosity. More landers to do different experiments, and Perseverance and Ingenuity, which we'll get to a little bit later. And all of these are helping with our search for life on Mars. And so what are the steps that we're looking at there? There's a few different stages building up to looking at, is there a chance there is life on Mars? And the first step is there water? Was there ever water on Mars? Then, is there currently water on Mars in frozen form? Then, is there currently liquid water on Mars? Then, do we have the ingredients for life, the chemical elements that we need for life? Then, do we have the compounds we need for life? These are kind of the more complex molecules, things like the ingredients of the food, but are just a bit bigger. And then, is there ever life? Can we see evidence of fossils or something like that? And is there current life? And now I should pause here and say we're not looking for green men, we're looking for microbes, tiny little bacteria. That is the life that we're looking for. Okay, so let's. So I saw a question here from Twigs, which is great. So I'll just jump onto that. Can we find out more about Mars' origins if we look at the history of Earth, since they're so similar? For sure, for sure. That's one of the things that we really try to understand both ways is how did Mars form and how did the conditions on Mars form and how did the Earth form and the conditions on Earth form? And because we've got two different examples, we can compare them to say, okay, what we know about Earth, because we've studied it a lot, can help us suggest what's going to happen on Earth, on Mars. And I'll show you some examples of this, of how we use the expertise from Earth to help us understand Mars. But also, learning more about what happened on Mars can help us understand processes on Earth or processes that may happen in the future on Earth. So it's really important going both ways. It's a great question. Thanks. And I'll get to the other question a little bit later. So let's look at, kind of related to that question, was there ever water on Mars in the past? And if you've got a guess, chuck it into the chat. Do you think there was ever water on Mars in the past? Well, what we used is one of these rovers. Now, the rover's got a few different sensors on board. You might be able to pick out some of them. It's got a robotic arm, which you can do to take some little samples, but it's also got two cameras on the top. And while it's just a camera, just like on your smartphone, it's actually really useful to look around. And so the way we use that, so I've got a few yeses coming in, we use that to look at the geology around. And this is where geologists, which are scientists that look at the different rocks on Earth, they know these different formations form only under certain conditions. And the picture you see here has got these ripples. These ripples are kind of those little fingerprints almost. They only form, as far as we know from what we see on Earth, under the presence of flowing water. So think of like a riverbed that's flowing and depositing some sediment, and it forms these ripples in the rock. So these are telltale signatures for geologists to say, hey, there was once flowing water on Mars. And again, that's using that expertise from Earth. Then the next thing, this same rover had a little bit of an incident at some point. When it was driving along, one of its wheels got stuck. So when the sand gets too soft, the wheel got stuck and it had to drag its wheel through the dirt. Now that eventually got free, so it was like, phew, it's still okay to keep going. And when it turned around, it found something really interesting. What can you see in this picture that looks a little bit different, a bit odd? You see this white mineral. Most of the surface of Mars is really red, but you see this white mineral that it dragged up as it dragged its wheel, as it kind of unexpectedly was doing a bit of a science experiment. And the geologists, again, from the experience that we have on Earth, know that is a silicate. So it's a type of mineral that only forms in the presence of water. So that was another really strong telltale signature that there was once flowing water on Mars. So we have a tick there. And I'll get to some of these questions at the end as we go through. There's some great questions coming there. Thanks. A fossil, not quite a fossil, but it's an indication of life on Mars with those ripples. So the next question is, was there water ice on Mars? But not just was, is there currently water ice on Mars? Because that's kind of an easier place to find because Mars is actually cold. So we want to see, is there any water in any form on Mars right now? And that was one of the big missions of this lander, the Phoenix lander. Now, can you guys tell probably what its main little instrument there is? Is it maybe this robotic arm coming off the end? And that's it. What do you see on the end of the robotic arm? It's a scoop. What do you think it's going to do with a scoop? I think you can probably all guess. It's going to dig. And what was it trying to do? To see if there was ice under the surface of Mars, protected by a few top layers of dirt. It's going to dig under with the claw thing. Yes, that's right. And it's going to see, is there ice there? And is there ice? There was. So as you dig under the surface, they found this. You see this white surface here. This was solid frozen ice, just kind of 5-10 centimeters under the surface. And so that was a really, really big moment to confirm that, yes, there's currently water ice on the surface. And that discovery has led to more and more exploration of Mars. And some orbiters, these are robots that go around Mars, have taken different measurements. And then we now even have a global map of where we think water is under the surface, frozen water, that is, with these colors as different depths. So this is like if you see a map of Earth, you'll see it out in this rectangle. This is the same thing, but for Mars, where the colors indicate how deep under the surface do we think water ice is. And so you can see the purple is a little bit more accessible because it's closer to the surface. So this would be a map you might use if you were planning your habitat on Mars, where you wanted to be near somewhere where you could go mine some water, which is a really important thing for humans. So yes, there's lots of frozen water ice on Mars. So that's really exciting. And so we have a tick. Yeah, and you can collect samples with that as well if you wanted to do some experiments if we got to go there. So the next step is liquid water, and we will actually get to collecting samples a little bit later on. So that's a good comment, Barbara. So the next step is there liquid water on Mars right now? So we saw there's evidence that it was definitely there in the past, but what about right now? So what we can look at is different changes in the environment, because if water's liquid and flowing, it can affect the environment around it. Think of it like a river or a beach or a lake. There's changes in that environment. And so what we look at here, this is a picture of a side of a cliff from a satellite around Mars. And there's these little black streaks that come out of the bottom. They're a little bit kind of peculiar, let's say. And what we see from season to season is they change. So on the left, you see there's kind of one black streak coming down. On the right, there's kind of a fork with two different black streaks coming. And so what we think that is some kind of melting over different seasons that leads to a flow of water down that slope. It could be really, really salty water, so it flows in a different way, but it could be something completely different. But we think it might be evidence of flowing water on Mars right now. But we don't know. We haven't been able to get close enough to this to really understand more. So this is still a question mark. So we'll get back to that. So remember that these are called recurring slope lineae, which is a fancy way of saying weird lines that change. So let's just remember, we don't know about current liquid water on Mars, but let's get back to that later. Now, are there the ingredients, the food for microbial life on Mars? So who has looked at a periodic table of elements before? Who's been to like a science classroom, or maybe seen it from one of their siblings going to a science classroom? You get this big table up that has all the elements. Some of them you might know of, like oxygen, you've heard of the O here. Maybe you've heard of helium if you had the balloons that float up. So this is something you'll get to in science class in high school if you haven't looked at it already. Now, on this periodic table of elements, there's a few elements that we know are really key building blocks for life, at least for life as we know it. And so they are carbon, nitrogen, oxygen, which we breathe, so that's really important, and phosphorus and sulfur. So these 5 elements are something that's really important. So if there was to be life as we know it on Mars, there would have to be these elements. If these elements weren't there, then we think it wouldn't be possible for there to be life there. So how do we normally look at these elements? We use some type of microscope, some type of scientific instrument. Think of the stuff you might have in a science lab. So we could use that to look at the different elements that are present. But wait, it's on Mars. How do you bring the stuff from Mars to the scientific instrument? That's going to be really hard. It's a whole planet. How are you going to bring it over to our lab? Well, you don't. We send a lab to Mars. And welcome the Curiosity rover. It's a rover that's about the size of your car or your family's car, if you have one. And it's got a whole laboratory on board. It's a big robot with a big robotic arm, which I'll show you soon, but all on board is different instruments. So it's basically a driving laboratory. And it's got this robotic arm out the front, which you can use to take samples. Someone was mentioning in the chat just before. And then those samples it can put into its laboratory instruments on the body to analyze and see what minerals are there. So that's really cool, but how do you tell it where to go? How does it know where to go to take the samples? Because if it was just sampling randomly, it might not really get anything. So that's what we call operations. How do we drive the thing on Mars? Now, does anyone think we might just use an Xbox controller to drive it on Mars? Or some other type of radio controller? That would be fun, I admit. That'd be really cool. But unfortunately, we can't. Unfortunately, it takes at least 8 to 20 minutes to send a signal one way to Mars. And then it's got to come all the way back. It'd be like playing Mario Kart and you press left, and then half an hour later, you can see it turning left. And by the time that you've done that, it's probably already crashed and the race is over. So we can't quite joystick it like you might think we're driving a remote control car. So what we do is we have a whole operational team and we play one day at a time. What happens is the robot sends information back through the Deep Space Network. For the Australians out there, this is part of the Deep Space Network is antennas in California and Australia and Spain. So some of the information from Mars comes through Australia and comes to mission control in JPL. This is for robotic exploration, not for human exploration. And from there, the team uses images like this. These are stereo images that are looking on both sides. And it uses that to build a 3D map that it can then simulate how the rover is going to drive through the environment. This is so the engineers can test, can the rover drive in these places? This is a very similar 3D environment to what you guys are doing in spacecraft. So here's an example of them simulating a drive for the rover. And then what it also does is we combine all these images and then we build this VR environment for scientists to walk around. And then the scientists can use that as a collaboration tool to decide where should we send the rover. They have this 3D environment and then they walk around in augmented reality. So they've got HoloLenses on, similar to what you might be doing in spacecraft. And then they go and discuss, work together as a team. Space teams is a good way to do it. They're a space team for space science. And then they pick the rocks and they go, okay, I think that's the place we should send the rover to go and take a sample because we think it's really interesting. And they're geologists, they're scientists that understand these features. And so, do you think we found these elements? And someone was mentioning programming, Clifford, for doing sending on Mars. Yes, when we actually send the commands up, it's all programming. And it's all lines of code that we're sending to the rover to tell it what to do once the team's decided what to do. It's a great comment. And it's autonomous a little bit as well. We can get into that in the questions later. So yes, I think everyone's saying there, we did. This is an example of, or this is a picture of one of the samples that the rover found, guided by the team of scientists and sending the commands up. And they found, yes, we found all of these elements on Mars. So great, that's a tick for the ingredients on Mars. What about the organics? Now, organics is a kind of a combination of these ingredients. Think of it like we've got the ingredients going into your food and then there's the actual end dish. But these particular combinations of ingredients are really important to how we understand life. So this is DNA, and DNA is made up of 4 amino acids that you see here. If you haven't gotten into it too much yet, that's fine. But these are combinations of these elements where every corner is a carbon and all these letters are oxygen or phosphorus. And basically, these are the building blocks of DNA, which is the building blocks or the instruction set for life as we know it. And what we want to see is, are there types of compounds similar to this that combine these elements and these types of structures? Not necessarily these specific ones in DNA, but things similar. It's kind of like the building blocks towards DNA, do they exist? Because that means they're getting closer to conditions that could support the formation of life. So again, we do operations to work out where to go, but there's some more that we want to do to make the robot autonomous, as someone mentioned before. So firstly, the rover's got some really cool instruments to help it assess the chemical composition of rocks from a distance. And so that helps to do things a bit more efficiently. And it's a little bit scary because it is a car-sized robot driving around with something very special. It has a laser. It's a laser on a robot driving around. How cool is that? Maybe a little bit scary if there are actual Martians there, but really awesome to be able to have. And what it does is it kind of vaporizes the rock and then can read back the reflection to see what chemicals are there. So you can see on the left, this is the laser that it has. We call it the ChemCam. And you can see these laser dots. This is where it zapped the rock in different places to see what the mineral makeup was. So normally we can command that to say, okay, zap this rock, zap that rock. But what if it could do it autonomously, like some people suggested? And some great questions coming through too. I'll get back to some of those at the end. Thank you. So what it does is we do it autonomously. So the images that the rover sees, these are the rocks it sees, it processes them to pick out rocks that it thinks might be interesting. So you can see it's outlined some in red, it's picked some in green and some in yellow that it thinks are really more interesting ones to zap. And so what we do is we just tell it to drive and then zap rocks with a laser that it chooses to be the most interesting, rather than waiting for it to send the images back and for us to choose. And with this method, it's able to get a lot more science return, which means it's able to find more interesting things in a shorter space of time. So we can get closer to finding the rocks that will tell us to answer the questions that are looking for life. So this method has really helped us to learn more and more about science and the rocks on Mars. And eventually, Curiosity, one of the bigger rovers, was able to take a sample here in one of the rocks, was able to find these organic compounds, these combinations of the elements that are the building blocks for life. So tick, we've found complex organic molecules on Mars. So we've got the food, we've got evidence of frozen water and past flowing water. There's maybe current flowing water. So almost there. Now, what about life? Was there ever life on Mars? Is there currently life on Mars? Well, we don't know. We're still working on that, and I'll get to some of the things we're doing next. But let's just jump back to the liquid water on Mars and these recurring slope lineae, if you remember them. This was one of the recent missions launched to Mars. Now, if you've seen this before, that's great. If you haven't, this is probably going to blow your socks off a little bit. This is live footage from Mars. Well, this current footage is at NASA of the latest rover coming into land. So here it deploys a parachute to slow itself down when it's high up on Mars. And then once it gets slow enough, it deploys that parachute off. It drops off the back shell, and this is the camera looking down, which it's using to navigate. And then eventually, it will go onto rockets as it gets closer down. So you can see the different regions it's going here. Now it's dropped off the parachute, and it's flying around on rockets, just having to navigate itself down. And with this camera looking down, let's imagine you had your like a phone with taking images down, and you're using that to work out where you are, but also to pick a good landing site that's away from rocks or big slopes. And so it's using that to divert away from hazards, to track how it's moving as it gets close to the ground. Now see if you can guess when it's about to land. It's kind of hard to tell. It looks kind of similar the closer we get. But as we get closer, you'll start to see something that's quite different. There's dust blowing around. And then we're going to split to a different view. And what's going to happen is what we call the sky crane maneuver. So on the top left, we have the sky crane, which is rockets, and on a tether holding the rover on the bottom left. That's to keep the rockets safely away as it gets to the ground. And the wheels of the rover are going to be its landing gear. It's going to land on those wheels. And then when it does, it's going to cut the tether and it's going to fly off. It goes crashes somewhere, but we don't really too mind about that because we want the rover there safely on Mars. And everyone's obviously very excited because that's all really hard to do. And here it is on Mars. Hey, what's that on the ground next to it? Can you guys see that? It's looking at something. What is that? You see this thing here? That's not a rover. How did that get there? That's the Mars helicopter. So this is Perseverance, the rover. Again, that's about the size of a car. And this is the helicopter. The helicopter took a ride like a kangaroo Joey in the pouch of a kangaroo. It took a ride on the belly of Perseverance. So here it is on the belly, and it had this little pouch, you could say, as a dust shield to keep the dust away. And then eventually, when it was ready, it was deployed off. So here it is, dropping the helicopter down, dropping it off, and then driving away. It got tested out to just check that the rotors were spinning, to say, okay, yep, I'm free to fly. You can see a solar panel on the top to charge its batteries up. And here it is, the first flight. Like, what are they cheering about? They're very excited about something. Can you see what they're excited about? This graph. Have you guys ever been that excited about a line on a graph before? I think I have, but I really like math. But what is this graph? It's an altimeter. So that says the axis here is how high the helicopter is, and the x-axis is time. So what does this line represent? What does it mean that it started here, it jumped up to about 3 meters, and then fell back down and then was flat? What do you think that means? Any guesses? It means it flew. This is it powering up. This means it got off the ground, so it's flying. And the fact that it comes back down to roughly the same place means it landed. So this was the first confirmation that this team got that it actually flew. And yes, they're the most excited I've ever seen anyone about a line on a graph. But that's what engineers are, and that's what we get from Mars. But eventually, we did get the images back, and you can see this here. This is the flight taken from the rover as a video. And yeah, great answers on the questions, everyone. You guys got it really well. So here it is spinning the rotors up. And once it gets up to speed, it's going to start to take off. And there it is, flying on Mars, the first ever powered flight on another planet. Does a little pirouette and then comes back down to land. So this was a really big moment for demonstrating that we can fly a helicopter on Mars. I'll go for just the zoom in so you can see the takeoff and landing. There it is taking off. And it goes out of shot. This is the zoomed in version. And Kiesh is asking, how long does it take the information to get down to Earth? Depends. The time it takes for the signal to get from Mars to Earth can be 8 to 20 minutes. But the helicopter has to talk to the rover, and then the rover has to talk to a satellite that's going around Mars, and then that has to talk to Earth. And so that can normally take several hours for it to get through to there. And this was kind of like what we call a Wright brothers moment, or we like to say. Wright brothers were one of the first people to have powered flight on Earth. And so we kind of got the same thing on Mars. Now, same question again, how do we operate this? Now, I said before we can't joystick it. So what we do, and you can see here, they're just getting data back. They're not even getting images back. So there's no way we could fly it. What it does is it's autonomous. It has to fly autonomously, and it uses these images looking down to do that. So this is the camera it has looking down, looking at its own shadow and some tracks from the rover, which is really cool. And as it flies, this is what it sees. And what it's doing is it's tracking the movement of the features in the image. So maybe you can see a rock that's moving from right to left. And that tells you you're probably moving to the right. And it's using these images to see, okay, how it's moving around, as well as some other sensors, a sense that tells it how high it is. And then it uses that to track its movement and go to where we command it. But otherwise, it's fully autonomous. We just tell it where to fly. Cassandra's asking, will we try and make bigger helicopters in Mars or other planets? It's a great question, and you've guessed ahead what I'm going to be suggesting. So we'll get to that soon, and I'll answer that question. But now the helicopter was planned for 5 flights to demonstrate can we fly on Mars. It's now done 33 flights. It's very much exceeded expectations, and it's continuing to go along. This is the flight path it's done. It started here. It flew down here to do some science scouting, and it's gone back across here. And what it's doing is following the rover. The rover is the white line. That's the path that Perseverance has taken. And it's coming up here to do some of its science mission. And what the helicopter is doing is to scout ahead. And it does that by taking pictures like this. So it flies around and takes these beautiful color pictures. Just imagine flying up with a camera phone. And those pictures help the scientists plan where to send the rover to go and do its mission. We're also able to do things like scouting maybe the recurring slope linear. Maybe we could get a future helicopter that's bigger. It's got the cameras that could go up and take some pictures of this. So we're not quite near these things, but that could be a really exciting future mission to answer, is there liquid water on Mars right now? But for the moment, it's doing scouting. So this was a picture of the descent stage. So there's a parachute here, and this is what we call the back shell that protects the rover while it's flying through space. It was able to go take pictures to see what happened when this which was jettisoned high up during the landing, when that crashed on Mars. It's supposed to crash on Mars, that's fine, but we learned from it by taking these awesome pictures. And then recently, we've got some different challenges. Even though it's doing 33 flights, there's always something weird that happens on Mars. Can you guys spot the weird thing in this video? Because this is the most recent flight. It takes off, and then it's flying along. Did anyone spot the odd thing there? or start it again, look at the bottom right of the video. Can you see something flapping around there? It's a hitchhiker. What is that? It's a little bit of some type of material, maybe some debris from the parachute or the landing system, that's caught on the leg and thankfully fell off then. But very unexpected to have that on Mars. So always different surprises and challenges that are coming up. Nice spotting of people in the chat. I see a few people got that. And now to one of the comments before, can we get a bigger helicopter? Well, that first little rover I showed you a while back, and I know we're getting close on time, that was so successful it led to bigger rovers, which led to even bigger rovers. So maybe this small helicopter will lead to an even bigger helicopter in the future. So hopefully we'll see. However, there is one next mission that we already know is planned, and that's this mission here. It's called Mars Sample Return. And this is the main mission for the Perseverance rover. So remember when we were saying we send the laboratory to Mars, and that's how we can look into some of these elements? Well, to answer the questions of was there ever life on Mars, if we can find some biosignatures of life, we're going to send Mars, wrong button, we're going to send Mars back to Earth. And no, don't worry, we're not going to send the whole planet back. We're going to take samples, little tubes of samples that will then come back to Earth so we can have really powerful, big scientific instruments to look in more detail at those rocks. And so that's the mission of Perseverance, to take these samples. It will take them back to a lander, which has a robotic arm. And that lander will put the samples on a rocket, and the rocket will launch it into orbit around Mars. A satellite will catch it in orbit and then head back to Earth and drop it off in a desert somewhere. So it's a pretty ambitious mission. It's got a lot of things to do. But one of the things about it that's exciting from a helicopter perspective is that there's a helicopter plant, this little guy you see on the left here. That helicopter is a backup to Perseverance. So Perseverance will drop some of these sample tubes. They're about the length of a pencil and about the thickness of like a glue stick or something. And the helicopter will go and fly and pick up these samples that Perseverance dropped. It's got a little robotic arm to pick them up and bring them back to the lander. And that's the next helicopter is going to be coming up, about the same size as Ingenuity. So some really exciting things there. So given we're getting near the time, I'm going to skip forward a little bit and jump forward just a little bit of my background. There's a few questions there. I can get back to these slides before, but one of the questions people might have is how did I get to where I am now, where I'm an engineer, a robotics engineer at JPL. So I grew up in Australia, and in grades 4 and 5, I wanted to be an Aussie rules footballer, and I really liked Lego and Star Wars as well. In high school, I really liked science and mathematics. I really liked understanding how things worked. And when I was thinking to go to university, I was pretty sure I wanted to do engineering because I felt engineering was solving problems with maths and science. So it's a really cool way to use what I liked just to solve problems and make the world a better place. But I also liked windsurfing and wanted to understand how sails worked and how fins worked in the water. Plus, I still like Star Wars. So what I did was aerospace engineering at the University of Sydney. Got to learn about controlling aircraft with autopilots, got to learn about controlling robots and flying around, which was kind of similar to controlling aircraft. And that led to an opportunity to do a PhD, which is a degree after doing your main degree in university, to learn more and more about controlling space robots. And that's where I got to do Zero Robotics, which you see on the right, where that's the code written by high school students is controlling these robots, these NASA research robots, on the International Space Station set up by astronauts, which is super cool. Then I got to do an internship at the NASA lab I'm at, doing some stuff on controlling drones for high-speed flight, and did a postdoc, which is a job after a PhD, and then was able to get hired after that. So I'll pause there, given we're getting near the time, and I can jump to some questions, or I can go back to some of the other content there. Josh, I can just dive into the questions or whatever you prefer.
Yeah, I love that you were answering questions as you were going. You're the first speaker to kind of do both the presentation and live answering, and it was awesome because the students were very engaged. So thank you, Ben, for that presentation and the stories. So I think let's start. Christy, how about you kick us off with the question that we've gotten pre-submitted, and then I'll go to the live.
Yeah, absolutely. And then I have some questions too.
Oh.
All right, we have Ethan from Australia wants to know, what challenges do you face while working with robotic technology?
Lots of challenges, and but very similar to some of the challenges you might be facing in space teams. One thing is there's many different parts to a robot. Just think of it like what if you have to do a certain job, like maybe you have to go out and dig up a certain rock from somewhere. You're pretty good at that, but we have to make the robot do everything you do. How do you walk over the terrain? How do you know where to go? How do you know where you are? How do you know what's around you? How do you dig? How do you work out where to dig? And how do you communicate to other people you might be working with? And we have to make all those things work and work together. So there's many parts to make a robotic system work, and that's one of the big challenges. And every environment's a little bit different. And so what might work somewhere may not work somewhere else. And so there's always new challenges specific to whatever challenge you're doing. And it might be similar to what you're doing with a habitat. There's many parts of the habitat that have to work together for it to be functioning well all together.
Several of the live questions you got was about working at NASA. Can
Mhm.
you talk a little bit about your experience? What's a day in the life of working at NASA?
It's very diverse. I have my own experience, but there's people in all different types of, I guess, professions that work at NASA, from people who are artists working on different things to a scientists who are looking at investigating stuff in the lab, to people who are operating spacecraft on Mars. So, at least at currently, my day to day is sometimes I operate Ingenuity, which I can see. Let's clean that just up here.
Thanks.
So I work with a team where we look at the data that comes back down from the helicopter. We work out what we want to do for that day. Maybe we want to send it on a flight. And then we prepare the sets of commands. Just think of it like an instruction set or a recipe that we will then send up to the helicopter for it to do whatever we want it to do next. So that's the operations side. Then other days I might be doing a lot of programming. We might be developing a new robot to go and explore on the moon. And then that might be programming different algorithms to help it work out where it is or for it to coordinate in a team. And that could be everything from the day to day, might be just working with other people, talking to my team and working with the team just like you are to plan out what we're going to do, how we're going to make changes, and then we go away and work on the different parts and then combine them together.
I'm going to sneak in one of my own now. I saw, I think it was the Perseverance had taken like 33 flights or something. Is there a goal for each robot for how many hours you would desire for it to log? And what happens to them? Do you drive it to the wheels fall off? Like, what do you do with that when you're done?
Yeah, great question, Christy. So each robot that we send has what we call like a prime mission. So we absolutely have to make sure we get this mission done. And so for Ingenuity, for the helicopter, it was just to demonstrate that we can fly on Mars. So its main mission was 5 flights. And most of the team were only really cared about the first flight, so can we fly? Um, and then once it keeps working, depends on what the goals of the mission are. And so normally, if it's still working on Mars, it's incredibly valuable to have a robot that works on Mars. So we keep using it for as long as we can. And we'll keep going until it doesn't operate anymore. So, for instance, the Spirit and Opportunity, some of the smaller rovers, they were designed for 90 days and they lasted for 10 plus years.
Wow.
And so
Mm.
they went far beyond expectations. And part of it's because we want to make sure it works for that mission. But we don't know everything, so we're very conservative. And so if it's not as bad as the worst case we expect, then it might last for much longer. And so Ingenuity, for instance, has very much exceeded expectations, and it's still going strong. 33 flights in, and we hope to keep it going for longer. Perseverance, on the other hand, the rover behind me, that's got a longer mission plan, so multiple years that it's planned for, and that's taking the samples to eventually send back to Earth. But then again, once it's done its main mission, if it's still working, we're going to keep sending it on an extended mission to go and do some more science and learn more about Mars.
Yeah, and follow-up question to that: did the team of people working with those particular robots stay the same, or whenever something is supposed to last a year and it lasts 10 years, do you go through different team members? I'm sure.
Yeah, there's some people stay on the mission for a long time if it's a mission that extends, but there's a lot of people that we bring new people on to learn, and people transfer their knowledge if they want to go on to another project or if they want to go on to do a different role. So it tends to be a fair bit of rotation with some people staying the same, but enough of people that stay on the mission for the long term that they can train up the next team that come on board.
Awesome.
I actually just got a question that I thought was fun. Do you ever think the rovers will all meet each other on Mars?
That'd be very cool. I think maybe if there was an incentive to do so, they're quite spread out because we don't have that many rovers on Mars. So when we plan the science we want to do, because all of this work is all for the science to learn more about Mars. And so if we already have a rover in one place on Mars, then there's not going to be that much more science if we go to the same place. So we want to go to a different area on Mars. So they're kind of spread out, but maybe if they last for a long time and there's a goal to, we might be able to get them to meet up on Mars. But definitely Ingenuity and Perseverance, the helicopter and rover, they have to stay near each other because Ingenuity can only talk to the rover. It can't talk back to Earth.
Oh, okay. And then I want to ask a second question here from Clifford, which is more about your personal story. What inspired you to do this job?
Yeah, thanks, Clifford. So part of what I was saying before, I was really interested in doing engineering. I liked space side of things. I was really inspired by that. And the other thing that really kind of motivates me for what I'm doing at JPL is the the goal of everything we do here is the science, as I say, and the goal for that science is to expand what humanity knows, to expand the boundaries of knowledge of humanity as a whole for humanity as a whole. And that's a really inspiring drive of everything that we do at NASA, where it's not to make money or it's not to make one country more powerful than the other. It's to really expand what humanity knows for all of humanity. And that has many flow-on effects that we can't predict. Some that we can, that the technologies spin out, but that kind of for all of humanity drive to extend what we can do is really really inspiring, and that's really motivating. And also to be around people that are motivated by that is a really exciting place to be.
Yeah, it must be pretty cool to have everybody so mission driven, right? And all passionate. Like anytime I meet someone who works in space, like the speakers we've had share this like real passion for their job.
For sure, exactly.
Another question, a pre-submitted question from Indonesia. We know that foreign planets' atmosphere are filled with gases. What makes the space what makes the space robotics? How do you make sure they're still in good condition while doing the missions?
Yeah, thanks, Johan. It is a challenge. So it depends on which planet we're going to. So, for instance, one of the questions was, are we making bigger helicopters to go to different planets? There's a mission called Dragonfly that's going to go to Titan. It's a moon of, I think, it's a moon of Saturn, where the atmosphere is methane. And it's really thick atmosphere and it's very low gravity. And so that's a different challenge. Flying in methane is a different thing, but it's great for flying because it's very thick, so it's almost like swimming. On Mars, it's mostly CO2, and CO2 is it's what you breathe out. And so we have CO2 on Earth. You might hear it a lot in the news. It's something we worry about putting too much into our atmosphere. But it's also very thin on Mars. And so that has different challenges. It means it can get pretty cold on Mars because the heat doesn't stay in. For flying on Mars, it makes it hard because it's about 1% the density of the air on Earth. But thankfully, we're still able to fly, which we can get into later. But Venus is really challenging. That's very hot and very dense gases. And so you have to be very careful to design any system that goes to Venus to survive in that. Like landers last for several hours if they land on the surface. There's plans for airships that will float around the atmosphere, but they have to have very special coatings to protect it from the atmosphere. So we use as much as we know about the gases in different planets and really design the robot to be able to survive in that. But yeah, it's a challenge.
Silly question. Do we have a robot that has landed in Venus? I don't know these things.
Yeah, so several landers there's have landed on Venus. They don't last very long though.
Okay.
Again, because it's very very hot. It's kind of like the greenhouse effect gone to 100 times, where the heat just gets trapped in. So that's yeah, one of the challenges there. But yeah, we've had landers on Venus.
That's a good question. Okay, so I've been trying to keep all the questions. So I'm just going to end with this one. We have a lot of students that are really passionate about space. They're in space teams. They're getting to build planets and pilot their spacecraft. what advice do you have for these middle school, high school students that are interested in space exploration?
Yeah, first of all, super impressed with what you're all doing. It's a really cool program. I hope you've learned a lot. I hope you've had a lot of fun as well, and had a good time working with your teammates. Um, just know that what you're doing now is very similar to what we do at NASA. And so, if you really like this stuff, just keep going into it. If you want to go into doing something in space exploration, um, there's many pathways to get into there. There's many things you can do in space exploration, and really, you've just got to keep following what you're really passionate about and pushing really hard. So if there's an opportunity to do something in that area, or an opportunity to do something interesting and different, such as space teams, give it your all. Really, really put your effort into it, because then you'll get a lot out of it. People will see you doing great stuff. People will see you putting a lot of effort in, and that may lead to more opportunities in the future to do other programs. And maybe something else comes up, like maybe zero robotics, or something else where you can do a robotics competition if you're really into robotics. If you like the space stuff, there may be other activities out there, and look around for them, dive into them, work hard on your main schooling. But if you see these other projects around, really try grab those opportunities, give them your all, and you'll see more opportunities come. And if you keep going to that, your horizons will open, and then eventually you might see a pathway going to something that you're really passionate about long term.
Yes, I love that. Well, thank you so much, Ben, for joining us here as the final expert in our series of expert presentations. And I just want to give a final message here. You were talking about put your all in. Well, students, this is your chance. The final hours of space teams. You have a little bit of time left to continue working on that habitat, going back to any other missions, doing surface exploration. Reach out to the help desk if you get stuck, if something's kind of looking weird and you need a little bit of support from the space team's crew. And then tomorrow, we are going to have our award ceremony. A special guest there, Barbara Morgan, who is a former astronaut and teacher, is going to be speaking, which is really exciting. And then as you wrap up all the spacecraft activities, we want to let you know that there is a survey to complete on the learning platform, and it is required for you to get that final certificate of completion. So make sure you submit that, and we just want to know your feedback on what we can do to make this mission even better. So those are my announcements, and now I'm going to let the students go off and continue building, designing, exploring. Thank you again, Ben, for joining us, and goodbye for now.
Yeah, good luck to everyone. Thank you.